Welcome to today's webinar. This is the Keys to Successful DOE. My name is Shari Kraber, and I will be walking through this today with you. I'm happy to have you here. We are going to keep everybody on mute today, and if you have any questions, you can post them in the questions panel, and I will keep an eye on that. If I'm not able to address your questions during the webinar, I will send you an email as a follow-up to this. If you have additional questions afterwards, you are welcome to send them to our group address, which is stathelp@statease.com. This webinar, as well as all of our previous webinars, is posted on our webinars page of our website, as well as on our YouTube channel, Statistics Made Easy by StatEase. I am going to be referencing our YouTube channel a lot during this webinar. I have many references here, and so there are a lot of videos available for you to learn so much more about DOE, and I encourage you to go there and explore. So design of experiments is an art as well as a science. And over our years of teaching and doing design of experiments, we have identified some key concepts and tools that are really useful to and lead to very successful design of experiments. Today I'm going to be talking about a few key concepts for planning the experiment. That'll be part one of the session, and then some keys to analyzing the data. And all of this information is just going to be overviews and pointing you to additional resources, as 1 hour is just not enough time to go into these in depth. But I think building a general awareness of these things is the first step, and will just get you started on your journey. So we are going to jump into planning a designed experiment. And the four things we're going to be talking about here are defining your objective and how your objective helps you determine which type of design to run, the importance of good measurements of your responses, touching on the sample size or sizing the design, and finally we'll talk about the order in which you should run the experiment. So when people are trying to design an experiment, they're often immediately thinking about, the number of factors they can study and how many levels they want to test. But foundationally, you should be asking, what kind of information do you need from this particular experiment? And when we're talking about information, we're really talking about what type of polynomial do you want to be able to build from this, because it's that polynomial that is creating the equation. And of course, also, what is your budget? How many runs can you afford? So we're going to be talking about the strategy of experimentation at this stage. Are you doing a screening design? Are you doing a characterization design? Are you doing an optimization design? And so I have a couple pages to kind of define those further here. So you're going to choose a design that provides the information that you need. The strategy of experimentation consists of those three types of designs, where screening designs are done very early on if you really don't know anything about the process. These are not necessarily where you start, but they're often where you go back to when you realize you have a bunch of unknown factors that you don't know if they affect the process or not. So the design objective for a screening design would be to simply detect our main effects. Characterization designs are fuller, more generally have more runs, and they are designed to define the interactions in your system. And these are good when you kind of have a handle on which factors have main effects, but you need to dig a little deeper and find out, where are the interactions, which things combine together to give you the best process. And you should also be thinking about adding center points, which is a third level and can assess the non-linearity or curvature in the system. These two-level factorial designs for characterization are often all that is needed to fully optimize your system. But if you do detect nonlinearity and have that need for a more complex polynomial, like a quadratic polynomial, then you need to go into a response surface type of design. So what type of design do you need for each of those objectives? Well, if you are way up at the top and needing to screen out factors and just find out if they have effects or not, we'll first of all make an assumption that there are interactions in the system, but we don't necessarily need to identify them at this point. So assuming that interactions exist in a system, we need to use a design that keeps main effect information unbiased from two-factor interaction effects. That means we need to use one of the yellow designs, they're resolution 4, or a green resolution 5 design, or a full factorial would also work. What we do not want to use are a resolution 3, and they are notated as red in our design layout, or Plackett-Berman, or some of the Taguchi designs. Those designs would all bias your main effects with the under the cover two-factor interactions. So we don't want to use those, but use the yellow designs generally. Now for characterization, we would use a design that can properly estimate all of our two-factor interactions. These would probably be the full factorial or the resolution 5 or higher designs, or green or white designs, and definitely think about adding center points to have that extra test for nonlinearity. If your goal is optimization and you need or want to run multiple levels, more than just 2 levels, then you're going to jump into a response surface design like a central composite, Box-Benken, or an optimal custom design. Now, for those of you out there who are doing formulations, you might be working in the food industry or the pharmaceutical industry, or some sort of chemical type of industry where you're really working with the ingredients in a formulation, then you should not be on the screen for factorials or response surface designs. You need to be in the mixture design section where you can actually do mixture designs, and there are mixture designs for the screening goal, and then there are optimal mixture designs that take care of all the other goals. Now, why do I say use DOE software to design your experiment? So many people just think that DOE software is just for the analysis of the data, and that is so wrong. You need to use the software to actually build and design your experiment from the front. DOE software is going to give you choices from modern design options that could be better than those used by previous researchers in your field. Just using the defaults of the DOE software like Design Expert or Statis 360 are going to give you a better design than what you would create by hand or by using a template out of a textbook. The software is going to remind you to think about adding center points or doing something like blocking or adding replicates, all of these extra add-ons that are probably not something you're going to think about on your own. The software is also going to check power or precision so that you can make sure that you have the right sample size for your design. And it's going to give you that final design layout in random order. And so, I just named several topics that we're going to be talking about more here in this session. And then, of course, the software is going to allow you to copy and paste to Excel to easily add your response data in. From observation of people sending us data, we noticed that most DOE analysis problems are caused by errors or omissions made in building the designs. That says, if you build a better design, then the analysis of the data is actually going to end up being better. So design building is just as important as design analysis. Let's talk about your response measurements. The responses are the outputs, those key quality characteristics that are the goal of running the whole experiment. I mean, the whole goal is to get good data, right? So you're going to determine which responses will be measured and make sure that the measurement system is going to produce accurate results. Continuous numeric measurements are absolutely the best. This is what you want to strive for. If you're trying to fit a polynomial model, whether that's a straight line or a curve, a continuous numeric scale is going to be the best way to fit that data. Now, let's say that you can't, you don't have a continuous scale. Then my next choice would be to build a rating system. You can do a scale that's a 1 to 5 scale or a 1 to 9 scale that represents the range of your data so that you get things that score both 1 and you get things that score 5. You don't want to create a rating scale and then only use the 1s and 2s. That isn't going to be effective for modeling, and that actually falls into the pass-fail or any type of binomial response. And you see on the screen here that if you have a simple pass-fail response data, that is going to require 75 to 100 runs or samples in order to do the model fitting. It requires just a lot of data. And this is whether you're using ANOVA or you're using logistic regression or any of the other tools. Quite frankly, it takes a lot of pass-fail data in order to create a good predictive model. So everything that you can do to get continuous numeric is best, and then a rating scale would be the second best. Make sure that your results span the full range of good product to bad product in order to create a strong prediction model. Often people say, well, I only want my DOE to give me all good results. Well, then if you're only getting the good results, then you're not going to be able to figure out factor settings that predict how to get good. The model has to span from bad to good to really tell you what's going on. All right, let's talk about the sizing of a design or getting the right sample size. So you want to confirm that your DOE has enough runs to get results. And the way that you size a design depends on the type of DOE and that you have. So for instance, factorial designs, you may have heard we size for power. And power means the ability to detect an individual effect. The response surface and mixture designs are different. We don't size for power with those. We actually size for precision. And we want to estimate the ability to predict the average response with a specified amount of precision. So let's say I want to be able to predict yield plus or minus 1%. So that amount of precision, that's that plus or minus a certain percentage or value. So here is where I need to give you a reference. A great reference for this whole topic, definitely not enough time to cover it here, is a YouTube video, How Many Runs Do I Need? Using Power and Precision to Size DOEs. So I'll give you just a brief overview here, but mainly you're going to want to go to that additional reference. So for power factorial designs, we define the change in the response. What's the minimum change in the response that you want the DOE to detect? That is your signal. And then you also define the noise of that response measurement, and that's usually done using historical data, just calculating the standard deviation of the response. And we size the design to achieve 80% or greater power. Now for response surface and mixture designs, we use precision, and that uses the fraction of design space tool, or the FDS graph. And by the way, that is found actually under evaluation, design evaluation. So for that tool, we change from the defining the change in the response that we want to detect to changing the precision of the prediction. So it says we want to have a predicted response plus or minus some amount. So you decide, it's a business decision, you decide what is that amount of error, kind of your 95% confidence interval, what is that plus or minus amount? Then in addition, you need the standard deviation of the response, and you need to, again, size to achieve the fraction of design space 80% or greater. So I realize that the details on here are light. I'm just kind of telling you, basics how, but you can go back to that webinar to get more information on this. All right, let's talk about how do I order the runs. This is a frequently asked question. And of course, run order matters. It really does matter. And as you've all heard, randomization is best. But why? I was teaching a class last week, and we got to this topic, and this came up. Why is randomization important? Well, randomization protects against external things in the environment that might bias the factor effects. So let me give you a little bit of an example here. So let's see, this is our a set of runs. So the minus signs are low values and the plus signs are the high levels. And this is in standard order. So that means for factor C, I've got all the low values first and all the high values, high responses. So all the low values of C are run first, and then all the high levels of C are run second. Now, when we go to calculate our effects, our effect calculations are done by averaging the response data that we get when factor C is set high, and averaging the response values that we get when factor C is set low, and then we take the difference between those. Okay, so if the runs are completed in standard order, like shown here, or sorted by any factor, sorted anyway, you might sort by temperature, then this effect estimate is going to be equal to that factor effect plus the other unknown effect. So whether that's maybe a chemical degradation happening over time, or humidity change happening over time, or anything else that's happening over time, that extra thing is going to get piled on top of the non-randomized factor. So that means that that effect estimate is now not unbiased, and potentially it's wrong. You can get completely wrong effects, and that can mess up your data analysis. So randomization is best if you can. Now, what happens if you know you're not going to completely randomize things? Well, there's two different categories here, two different things we can do in our design to protect ourselves. So number one, let's just say that we have a variable that we are not studying, but it's also not constant. So for example, you take a 16-run experiment and you have to run it over 2 days, Monday versus Tuesday. Or you are splitting your design over multiple analysts to help you get the data more quickly. Then there's a tool called blocking that should be used in the design. You have to do this when you're designing the experiment so that it statistically reorders the runs in special groups to protect against bias from that variable that you're not studying. Okay, so that is something. It does not work to do blocking afterwards. If you see, oh yeah, I had to run this design over 2 days, I'm going to go back and put a block on it. Well, that isn't statistical blocking. That's just reordering your runs and trying to pull something out of it, but it's not statistically sound. Okay. The other way that you might be ordering things is if you have to change the run order based on a factor setting. Let's say temperature is very, very common, that we sort on temperature and run all the low temperatures first and all the high temperatures second. Then you have created a split plot design. And a split plot design sounds very scary, and you say, well, I'm not going to do a split plot design. Well, actually, you are doing a split plot design if you are ordering the runs based on a factor setting. The question is, are you going to do the split plot analysis? And you have to get it into the software as a split plot design in order to do the split plot analysis. It's a special analysis that correctly accounts for the hard to change versus easy to change factors. Now, again, that's a much bigger topic than I have time to cover today, but we have a YouTube video on that, split plot pros and cons, dealing with the hard to change factors. So I encourage you to check that out, look that up, and if you need help on this, you are welcome to email our stathelp@statease.com account. Above all, randomize. If you can't randomize, then at least use the proper tool to restrict the randomization, but set it up in the design of the experiment. Use the DOE software to design it correctly to make the analysis better. Okay, so those were keys to designing the experiment. Now, you've got the experiment designed, you've gone out and collected your data, we are ready to analyze the data. So selecting the model is the most important part of data analysis. Selecting the model is the data analysis. A couple of quick things. You only want to include terms in your model that are statistically significant, with the exception of also including terms that are required to maintain model hierarchy. And what is model hierarchy? Hierarchy means that if you have a child term, like an interaction like AB, if that child is in the model, then the parent terms A and B should also be included in the model. Another type of higher order term would be a B squared term. If B squared is in the model, then the parent term B also needs to be in the model, even if it's not statistically significant on its own. It gives it the parent terms give the model a base, kind of that starting point, and then the interaction or the squared term are adjustments from that base. So if you haven't put the base in the model, your model can be all over the place. And also then the model will not predict the same in both the coded units and the actual units, which is really a must-have. All right, so you choose terms that are statistically significant. Everything else gets pooled together and is used to estimate the residual error of your system. Your polynomial model is used to create model graphs, predict future results, and optimize your system. If the model is wrong, everything is wrong. So you have to have the right, good model. So I'm just going to give you a couple examples, one on factorial design and one on response surface design. We are going to focus on, in Design Expert, you analyze the data going left to right on these buttons across the top of the screen. You can choose a transformation, but we're going to start with no transformation. In a factorial design, we're going to use the half normal plot to select effects to include in the model. The whole purpose of the factorial or the half normal plot is simply to split your terms into two groups, the big effects and the small effects. And I'll just note that there is a YouTube video on this graphical selection of factorial effects that you can reference. I'm just going to show you a screen here. This is the half normal plot of effects. And you select only those effects that jump off the red line to the right. So they have to be off, I say below and to the right of the line. If they're to the left of the line, you don't select them. Those are not significant. But we are going to use these big terms so to create our ANOVA, and all the other terms are left in the residual. And a good rule of thumb is that probably only 20 to 30% of the terms are going to be significant. 20 to 30%. So the bulk of them are higher order terms and things that are not significant. Over selection of the terms in the model leads to incorrect p-values, because p-values are formed from the F's, and the F tests are basically comparing these selected terms to the unselected terms and doing an F test. So you need to have a good remainder in the residual in order to get good tests. Moving over to response surface designs, here you have both a fit summary that will give you a suggested model and a model screen and then the ANOVA. We're going to look at the ANOVA. So here's your ANOVA. Again, you want to only have terms in the model that are statistically significant. The term p-value should be less than 0.05, or C, factor C here, is not significant, but it is required for hierarchy with the AC interaction and with the C squared. So that is a little exception to the rule. It's in there for hierarchy. Then we also double check that lack of fit is not significant. So that lack of fit p-value is greater than 0.05. And we want the adjusted and predicted R-squareds to be within 0.2 of each other. And certainly higher numbers are better. There is a YouTube video on this, keys to analyzing a response surface design, that I would encourage you to go look at for more information on guidance in analyzing this. But the main things were, don't over-select your model. Residual diagnostics come by comparing the observed data to the predictions from your polynomial model. And the difference between the data that you collected and the predictions that are being made is called the residual. And those residuals should be free and clear without any remaining signal in them, no visible patterns. So we go through the basic graphs, the normal plot of residuals. The residuals you don't want any signal left in it, so they should just be normally distributed, a nice straight line. On the residuals versus predicted plot, again, no particular patterns. It should be just a random scatter up and down from left to right. And on the residuals versus run chart, there should be no points out of bounds, nothing outside the red lines, and no trends on this plot. So really important with your own data to look at the residuals versus run chart and make sure that there's no groupings and no up or down trends. And then, of course, my favorite plot is the Box-Cox plot, where it will assess your data, does some fast under the covers calculations, and it checks all the possible power law transformations, and it recommends something. In this case, and in most cases, it's going to say recommended transformation, none. Means you don't have to do anything. If it said log, then you would go back to your configure screen and put on a log transformation or a square root transformation or whatever it tells you. Basically, all you have to do is read the legend here and follow what it says. But this is a key to analysis. Pay attention to those residual plots, and especially pay attention to the Box-Cox plot and look for the need for a data transformation. Data transformation is going to improve the fit of the model, reduce the error associated with that model. That's what it's designed to do, is to minimize the error sum of squares. That's what's on that y-axis there. Now, part of analysis is also interpreting the results. And keys to interpreting the results go back to asking, what were the original objectives of the experiment? You'll want to review the model graphs. Looking at the interaction plot or the contour graph or the 3D, there's a lot of different graphs. But step one, ask yourself, which factors are not statistically important? Which things got set aside? How is this important? Is this information important to your business? Often it is just as important to find which things do not affect that response as it is to find which things do affect the response. Okay, then looking at things that do affect the response, what new process understanding do you get? How, how do some interactions change the response? Once you've looked at the graphs a little bit, then consider using numeric optimization. And numeric optimization is not what you always need to get to. There's often a lot of process understanding that you can get that you would overlook if you only use numerical optimization. So review your model graphs first. But then if you're going to look at numerical optimization, change the limits, change those default limits to reflect customer specifications. Also, people are always telling us that they get a lot of results, like they might get 100 solutions. That means that your process is robust to the limits that you set. So you might tighten up the limits to focus on a more optimal area. So tightening the limits is the way of reducing the results, but you might also just have kind of a robust area. So let me get to a picture on that shortly. First of all, two-level factorial designs are generally going to be interpreted using main effect plots or interaction plots like this. and they will usually direct you to a corner of the design space. So this optimal setting here, we had 3 factors significant, so we could show that on a cube plot right there, and the optimum is about a 90% yield. In response surface and mixture designs, you're going to tend to get contour plots, and you might view them in 3D surface. But this is a good example where if my goal for this particular response is simply to be greater than 80%, then my solutions in numerical optimization is going to give me all of these values in this corner. They are all above 80%. And you can see by the 3D that it's polynomial is actually turning down just a little bit at the corner. And so the maximum is going to be somewhere up here, but there's a big, broad range of good values. So the 100 solutions that you see are just going to be, covering this whole area. And so don't just dismiss that when you get, so many solutions. It's really a positive thing. And if you go back to the graphics, you'll see that, oh, there is a robust area in which I'm getting the results that I asked for. And if you want to get more, if you want to tighten up the limits, then you'll tighten up the optimization results. Whoop. So the numerical optimization, you can learn a lot more about that in our YouTube video, Multiple Response Optimization Unveiled. And it will talk about setting these lower and upper limits. It'll also talk about all of these other things, weights, importances, and such. This particular one shows my factor settings. All the red dots are the factor settings, and the response for the undenatured protein of about 80.5%. So after we analyze the data, create the polynomial model, we are going to interpret the model graphs using subject matter knowledge. Then we may use numerical or graphical optimization to find a sweet spot, narrow down the area to the region that you're really interested in. The final step of any experiment is to confirm or verify the results. Do these predictions work? You can't just publish your results without having done confirmation runs. So how are we going to do the confirmation of the results? Well, you can identify one particular spot, gather one single observation at the optimal settings, and and just say, oh, does it work or not? Well, my question is, does one run provide a good estimate of the process? Thinking about it, probably not. So let's go to number 2. Gather several observations at the optimal setting. Like, how many is several? 4 or 5 would be great. And then use the confirmation node. I'll show you that on the next screen. If the mean is within the prediction interval, then the model has been confirmed. A third method, which I'm not going to show, but I'll just point out here, is to actually run a small experiment around the optimal settings. So treat your optimal setting like a center point. Pick a small range for each factor and do a little designed experiment in that range. Then you can compare the predictions at the center point in the new experiment to the prediction interval that was calculated by the previous analysis. You might use this type of mini DOE to get some sensitivity analysis in addition to confirming the previous model. Okay, so where is the confirmation node? You will find the confirmation node down here under post analysis. It says confirmation. And step number 1 is to determine what location you want. By default, this will be the solution number 1 from your numerical optimization, but I would edit this and round the numbers to what you're actually going to do. Don't just leave it with, the 5 decimal places on each of these. Actually put in your real numbers, enter the factor settings, then collect the data. So I put in 5 runs here. So I've measured this undenatured protein 5 times. And then down at the bottom, a 95% prediction interval will be calculated based on an N of 5, based on a sample size of 5. So this is an adjusted interval that is correctly calculated for a sample size of 5. And if my average of the data that I collected in number 2, if that falls within this interval, then this will be black. If that average falls outside of this interval, it will turn red. The whole thing will turn red. And so it's really easy visual to see if you confirm your results or not. You can do multiple confirmations. There is a little arrow up here. If you click on that, there's an option to add location. And so you can add a second location, a third location. And so you can confirm multiple locations all at once. Okay, so let's do a little recap and then I will check for questions. So the keys to planning the DOE are defining the objective. What type of data do you want? And our objective is going to determine the type of design that we need. Measure your responses on a continuous numeric scale. Make sure that power or precision of the design is above 80% so that you know that you have a big enough sample size. And run the design in random order or design in any restrictions and randomization. Don't just sort it and think that that's good enough. You really want to design those in. Then in the analysis side, when you're analyzing the data, first select only significant model terms and those needed for hierarchy. Leave everything else in the residual. The key here is don't overfit the model. Then check your residual diagnostics and the box-Cox plot for any anomalies. Use your model graphs in combination with the optimization tools. Your goal is to gain process understanding and tell the story of the data. You really want to be able to show other people what's going on by choosing good graphs. And then absolutely go back to the process and complete confirmation runs to verify that the results are real. Let me check for any questions. So there was a question about the use of that thing called the prediction interval. There is a sliding bar between a confidence interval and a prediction interval. A prediction interval is not only used for individuals, but it's also used to provide the interval for the next prediction, and that can be a mean. Interesting statistical differences between tolerance intervals, prediction intervals, and confidence intervals. So that would be something to look into a little bit. But the prediction interval is in this application the correct interval to look at. Somebody asked about low R squareds. A low R squared means that you are only explaining a small amount of variation in your system, and it might mean that you don't have all the factors in the model. That, I mean, you might not have all the factors in the experiment. There might be other factors in the system that are also affecting things. Or it might be that the response measurement has a lot of noise in it, and you need to tighten up the method in which that response data is collected. It's not generally something that can just be fixed within the experimental analysis. It's usually part of the whole system. Another question asked about the desirability in optimization. Desirability is not a statistic that you're trying to optimize. Desirability is simply a mathematical tool of sorting the solutions that are given to you. So there is absolutely no goal of getting a desirability of 1. The desirability could be 0.5, and if that solution is the top solution presented, then it is your best solution. So I encourage you to go to the webinar that I referenced for multiple response optimization and look into that, and I talk about that in more detail. If you want to get a copy of this presentation, it will be available on our website under the webinars page within a couple of days. It's not there yet, but you can go there by Friday, and it will be up on our webinars page, and you can download it. I hope this session has just given you some things to think about. That's what it was intended to do, kind of an overview of a lot of different topics. And if you are interested in more DOE training, I encourage you to consider some of our classes. Definitely go to our YouTube channel and download more things. And this summer, we are going to be launching a new Essentials series of classes, and so you can keep an eye out for those, as well as our longer, more comprehensive training classes. I would like to thank you for being with me today and listening to this, and look forward to seeing you again in the next session.